Okay, so my name is Ilya, and I'm a postdoc in Flavio Fenton's group. And today I'll talk about the experimental description of period doubling patterns in cardiac tissue. So in our research, we are mainly focused on heart dynamics. And as you may already know, heart disease is one of the leading causes of death in the world. And also it ranks as #1 in industrialized countries. When you look at the statistics, we can see that the number of total deaths corresponding to cardiac-related diseases account for almost 30%, almost 1/3, and killing more people annually than cancer and stroke together. More specifically, in our lab, we study mechanisms of arrhythmia initiation, methods for arrhythmia control and prevention, and methods for arrhythmia termination. And today I'll be just focused on period doubling. So as our research is mainly experimental research, we do experiments on isolated hearts. So what you see in this movie is isolated rabbit hearts with normal sinus rhythm. So in order to understand arrhythmias, it's important to study mechanisms, of course, which underlie them. And so one of those mechanisms are related to spiral waves. So what are the spiral waves in cardiac electrical activity? So when you look at the normal heart response, that is normal heart rhythm, you could simplify electrical waves that travel along the heart as 2D planar waves. However, in the case of a spiral wave, spiral waves are self-organizing and self-sustained rotating electrical waves that cannot be terminated. And what happens over time is that they're unstable and they tend to break down into multiple spiral waves. And when that happens, ventricular fibrillation will be developed, which, if not treated, will lead to sudden cardiac death. So let me now show you some clinical experiment that we did. So what you do see here is dog heart fibrillation. And then, so many spiral waves are present, then we shock the hearts and we convert we actually terminate those spiral waves to just a single spiral wave that is happening right now. So we converted fibrillation to tachycardia, and then we shock the heart once again and completely terminated tachycardia and restored normal sinus rhythm. Okay, so what are the alternates? What do they represent? So as you think about a single cardiac cell, what you should expect is that with each next stimuli, the cell responds in the same way. There is no difference in action potential ratio from beat to beat. But however, at faster pacing cycle length, what happens is that a cell can accommodate that fast pacing rates in a way that alternates will be developed, which can be represented as changes in action potential ratio from beat to beat. And in this case, we call these alternates as period 2 alternates. And this can be nicely described with bifurcation diagram here on the right. So alternates are actually very known mechanisms for arrhythmia initiation. So what actually happens is that when the heart is paced, it's very, very fast. Certain regions, certain cells will accommodate in a way that alternates will be developed. And then it's important to understand that these alternates are not only alternates in time, but they're also alternates in space. So because of that, what happens is that there will be dispersion in conduction velocity, and dispersion in conduction velocity actually can lead to wave breaks. And then when that happens, there is a perfect trigger for onset of a spiral wave that happens in the middle region. And as already being said, spiral waves are not stable. They will tend to break up into multiple spiral waves, and that is where fibrillation occurs. So period doubling cascade is known way to chaos. So what we observe experimentally are not only period 2 alternates, but also period 4 and period 8 alternates, and definitely there is high periodicity, but it's hard to see experimentally. And what we postulate is that with higher periodicity, alternates tend to be less and less stable, then usually what happens is that they will break up to, causing some chaotic activity that is ultimately fibrillation. So let me talk now about experimental description of period doubling patterns in cardiac tissue. So what I showed you so far are the alternates in voltage. However, in order to understand arithmogenesis, it is also important to study dynamics of interstellar calcium because voltage and calcium are mutually coupled. So for that reason, we have designed and built a single camera setup that allows us to simultaneously measure voltage and calcium. And then for the measurements we used principles use optical mapping, where we use optical dyes, we stain the heart with them, and that's how we're able to measure responses. So this slide here illustrates our experimental setup. So you see here isolated hearts placed in a heated chamber, stained with optical dyes, and illuminated with LED colors. That's why you see these funky colors. So optical mapping technique is a really powerful way to visualize dynamics, but only on the surface of the heart. And what you see here is these animations are actually experimental data. So you see on the first one on the left, the vertical configuration, which corresponds to multiple spiral waves, and in the middle is a vertical tachycardia where you see only one spiral wave present. So it usually happens in biological systems. When you go more deeper and deeper into the subject, things always get more and more complicated, never simplified. So what happens also in our experimental studies is that we perform research. We perform experiments on many different animal hearts, and then starting from the rabbit hearts, we obtained alternates both in calcium and voltage, and more to say that alternates in calcium are more related to changes in the amplitude, while alternates in voltage are related to changes in NPD duration. So then what we did later is that we perfused. So in order to understand actually the causality between voltage and calcium, what we did is that we perfused heart with very low calcium that just kills the calcium activity, and in that case we didn't observe any activity voltage, which leads us to a conclusion that in rabbit heart is the calcium dynamics that actually drives voltage alternates. And then this movie here represents propagating waves from base to the apex at different basing cycle lengths. And as you can see, starting from 200 milliseconds up to 146 milliseconds, the waves are not looking anymore as planar waves. What happens, they curl around the regions because they're spatially distributed alternates. And then this curling can actually cause a breakup, and that's how the spiral waves can be generated. So this slide here illustrates alternates not only in time but also in space. So that there's clearly a difference between odd and even bits in APD and calcium amplitude duration, but there are also differences along the heart. And then this kind of complex dynamics can be a little bit better observed if you do 1D plots along some particular line, which is illustrated here, these figures on the left. So then we did experiments on pig hearts, and then what we observed, actually what we didn't observe, no alternates in voltage, no in calcium. And then currently we have no explanation why this happens, and we are even more puzzled because this doesn't mean that pig hearts cannot develop fibrillation. It's actually quite opposite. Pig hearts, fibrillation is very easy to initiate. And then to spice up the things at the end, we also did experiments on cat heart, and the cat heart situation is quite opposite. We did observe very prominent alternates in calcium, but we didn't observe any alternates in voltage. I can say that, for example, in the case of cat heart, it's very hard to induce fibrillation. Even if you do that, it is not so self-sustained. It usually self-terminates. So that will be I'm coming to the end of my presentation. So what I presented to you is what we do in our lab, and these are our main accomplishments. So besides the build-up of this system that allows us to simultaneously measure voltage and calcium, and then that we, for the first time, actually obtained, we were able to obtain for the first time isolation experimental data showing discordant alternates for calcium, and then we compared this experimental data with numerical models to discover that numerical models actually cannot represent our experimental iteration, and that is one of our future goals to see how we can improve theoretical models. So thank you very much for your attention, and I'll be happy to answer any questions.
So what happens in the pick guard as you increase the frequency, get more and more? At some point it just stops without going any doubling at all?
It actually doesn't respond in the overload, so it's kind of hard to kind of accommodate in a way that maybe there's some, as the wave propagates, it will be blocked in a certain region. So if you're trying to find a way to go around, so that's what happens. And so the dynamics becomes more and more complicated, and usually when the wave, it must happen that the wave will occur somewhere, and then it goes to fibrillation. So the car basically cannot, if it exceeds certain kind of frequency, cannot give it anymore.